These are those are questions that are dealing with charges moving between parallel plates. So the first case will be when the charge is moving collinear with the electric field that is created between the two parallel plates. In this case, what we have is we have an electron that is accelerating from rest. So the initial is equal to 0. And through a difference of potential of 120 volts. And what we are doing is we are looking for the final speed of the electron. We are dealing with the electron, which means that the mass of the electron is 9.11 times 10 to the power of negative 31 kilogram. And the charge of the electron is one elementary charge is negative, but as a magnitude is one elementary charge, which is 1 times 1.60 times 10 to the power of negative 19. Okay, so when we are dealing with cases in which the particle is moving collinear means either in the same direction or opposite direction, but on the same line, we are using the conservation law of energy. So let's draw a situational diagram of this problem. So we have two parallel plates, and in one of them we have an electron. And the electron is at the rest, but then it is accelerating to the other plate with a difference of voltage of 120 volts. So since the electron is starting at one plate and it is heading to the other, that means that the plate that the electron is heading to is positively charged, and the one that was originally is negatively charged. Why? Because the electron is naturally going toward the higher voltage. On the other hand, what we have is that the electric field between the two plates is E, going in this case west direction, while the electron is moving toward the plate, positive plate. So this will be the direction of motion of electron. So as you see here, those two lines are parallel to each other in the opposite direction, but doesn't really matter. This is what I meant by collinear. Okay, so now the conservation law of energy on this case will be written in the form kinetic energy initial of the particle. It's either it's being between two parallel plates, though the electric potential energy between the plates is either added or taken away by the motion of the particle. In this case is added because the electron naturally goes toward the positive plate, and this is electric potential energy is equal to kinetic final. Now, since in this case the electron is at rest, we can say that kinetic energy is 0, and the electric potential energy between parallel plates is delta V times Q, and kinetic energy formula is 1/2 mass, and then what we are dealing is the electron times V final squared, and it is the electron. So now if we substitute what was given here, the mass of the electron and the charge, and the voltage as well, we'll find that 120 times 1.60 times 10 to the power of negative 19 is equal to 1/2 times 9.11 times 10 to the power of negative 31 times V final of the electron to the power of 2. Or you can use the formula as V final of the electron is equal to the square root of delta V times Q times 2 over mass of the electron. Okay, and on this case, V final will be, after you enter it in your calculator, will be 6.49 times 10 to the power of 6 meters per second. Okay, let's take a look now at a case in which we have an electron, or let's make this a proton now. Proton is accelerating through a potential difference of 20 volts. If the proton begins at the speed of 6.0 times 10 to the power of 4 meters per second, what is the final speed? Let's just delete this. Okay, so now we have a different situation in which the kinetic energy initially is not zero, has a certain value. So situational diagram on this case will look something like this. We have two plates, and in one of them we have a hole in which we will be able to insert those protons that are accelerating, proton beams or proton, just the single proton. And the initial velocity of proton is 6.0 times 10 to the power of 4 meters per second. Now, since the proton is accelerating, this is what it is saying here, then the natural flow of proton to accelerate, to not be opposed on, is to head toward the negative plate, which makes this a positive plate. Now the change of voltage between those two plates is 20 volts. So now let's, again, the electric potential, the electric field strength between the plates is leaving the negative going toward the positive, and the direction of the motion of proton, direction is in the same line, in the same way. So those two are parallel to each other, which means that those are collinear. Therefore, in this case, what we will use is the conservation law of energy. Conservation law of energy in this case will be something like this. Kinetic initial, and now if or since the proton is going naturally to the negative plate, the electric potential energy between those two will be added. So electric potential energy will be added to initial kinetic energy, and this will be equal to final kinetic energy of proton. Now, in your data booklet, you have that mass of proton is 1.67 times 10 to the power of negative 27 kilograms. Charge of proton is positive 1 elementary charge, but is 1 times elementary charge, which means that is 1.60 times 10 to the power of negative 19 coulombs. So then, the kinetic energy formula is 1/2 mass of proton times initial velocity of proton to the power of 2 plus electric potential energy is change of voltage times charge of proton equals to 1/2 mass of proton V final squared. And this is what we are looking for, is the V final squared. You can do this using a formula or a substitution. If you are using a formula, V final of proton will be the square root of, it's a large number, 1/2 mass of proton times VI squared plus change of voltage times charge of proton times 2, the whole thing divided by mass of proton. And if this is too confusing for you, then you go 1/2 times 1.67 times 10 to the power of -27 times 6.0 times 10 to the power of 4, the whole thing to the power of 2, plus 20, that is the change of voltage, times 1.60 times 10 to the power of -19 is equal to 1/2 times 1.67 times 10 to the power of -27 times the final squared. Enter this in your calculator and figure out what is the number. We got the final as equal to 8.62 times 10 to the power of 4 meters per second. And this is, even when you think about it, it is an accepted value because the voltage is not that high. And still the speed of the electron as it is reaching the other plate is greater than initial speed of the electron as it is entering the other plate. Okay, we'll bring another example and then we'll continue with it. So let's take a look at this question now. We have an alpha particle that is decelerating through a difference of potential energy of, let's make it 25 volts. If the alpha particle starts with a speed of 6.47 times 10 to the power of 4, what is the final speed? And this is the second part of this question, is what should the potential difference between the plates be to make the alpha particle stop? So the situational diagram in this case is, again, we are between two parallel plates. And in one of them, we are able to exert to enter an alpha particle with an initial velocity, in our case, 6.45 times 10 to the power of 4 meters per second. And as the alpha particle is entering between the plates, the question is telling us that it's decelerating, meaning that the speed is less, meaning that the alpha particle is not naturally going toward the other plate, but the other plate is opposing the motion. So that tells us that the plate that the alpha particle is thrown to is a positive plate, and the plate that the alpha particle is entering to is a negative plate. Good. Now, the electric potential or electric field strength between those two plates is going from positive to negative, as always, and the direction of the motion of the alpha particle is from negative to positive, so direction of motion. So since those are collinear between each other, what we will do is we will use the conservation law of energy. So it's starting with the kinetic energy, initial kinetic energy of the alpha particle. And now, since the alpha particle is opposed by the plate, you can think of this way, since the alpha particle is opposed by the plate, it is slowing down, and the amount that is slowing down is the electric potential energy between the two plates. And the fact that it's slowing down is represented by taken away from kinetic energy. And this will give us the final kinetic of the alpha particle. So in the case when the particle or the ion is not naturally going toward the plate, as thinking of positive toward the negative, or negative toward the positive, negative charge toward the positive charge, positive plate, then, so it's not going naturally to, then the electric potential energy is taken away. This is how we write the conservation law of energy. And then we'll have 1/2 mass of alpha particle, initial velocity squared, minus delta V times charge of the alpha particle, 1/2 mass of the alpha particle, V final squared. So now in your data booklet, what do you have in terms of the alpha particle? Is that mass of the alpha particle is 6.65 times 10 to the power of negative 27 kilograms. And charge of the alpha particle is positive, but it is positive 2 elementary charge, which means that it's 2 times 1.60 times 10 to the power of negative 19 coulombs, or 3.20 times 10 to the power of negative 19 coulombs. And in our question, the change of voltage is given as 25. So we can say that final velocity of alpha particle is the square root of 1/2 mass of alpha particle V initial squared minus change of voltage times times the charge of the alpha particle. And this is, the whole thing is multiplied by 2. And it is divided by mass of the alpha particle. If this is bothering you, you can plot in the numbers as 1/2 times 6.65 times 10 to the power of negative 27 times 6.45 times 10 to the power of 4, the whole thing to the power of 2, minus delta V times charge, which is 3.20 times 10 to the power of negative 19 is equal to 1/2 times 6.65 times 10 to the power of negative 27 times a V final of the alpha particle square. Enter this in your calculator and you will find the value of the V final. So I have here that V final is equal to 4.19 times 10 to the power of 4 meters per second. And you were expecting that this will be lower than initial because it is, the kinetic energy is quote unquote eaten up by the electric potential energy between the two parallel plates. Now, the second part of this question is kind of interesting because we are saying now, what should the potential difference, which is delta V, be to make the alpha particle stop? So imagine now that we can increase the change of voltage between those two parallel plates and make the alpha particle to stop moving. So in that case, what we would have is that again, if we are using the conservation law of energy, we'll say that the kinetic energy of the alpha particle initial taken away from the electric potential energy will make the alpha particle stop, so will make it zero. Or in other words, the kinetic energy initial is equal to the electric potential energy between the two plates. Or 1/2 mass of alpha particle times initial to the power of 2 is equal to delta V, and this is stop. Okay, delta V that will make the alpha particle stop times the charge of the alpha particle. So in terms of the formula, the change of voltage that will make the alpha particle stop will be 0.5 times mass of alpha particle times initial to the power of 2 over the charge of the alpha particle. Or if this bothers you, you can figure out in plotting in the numbers. So 1/2 times 6.65 times 10 to the power of negative 27 times initial was 6.45 times 10 to the power of 4. The whole thing to the power of 2 is equal to the change of voltage that will make the alpha particle stop times 3.20 times 10 to the negative 19 coulombs. That is the charge of the alpha particle. So enter this in your calculator and see what do you get. I have the voltage that will make it stop is 43.2 volts, the difference between the two, and you should have the same value. Okay, let's bring another question and see now if the particle is stopping, where is it stopping, and all that information. Okay, so let's take a look at this question here. We have an electron beam that have a speed of an initial speed of 3.43 times 10 to the power of 4 meters per second. And it is entering between two parallel plates that have a change of voltage of 120 volts. And they are apart from each other at 4.56 times 10 to the power of negative 2 meters. So now the electrons are entering through the positive plate and are heading toward the negative plate. Well, the electron will reach the other plate, and if not, where is it stopping? So the situational diagram will be something like this. We have two parallel plates. In one of them, we have a hole in which we are able to exert some particles, and in this case, the particles that we are exerting, that you are putting in, are electrons. So the electrons are heading toward the negative plate and are going through the parallel plates through the positive plate. Now the electric field is again leaving the positive and going toward the negative, and now the electric field strength is magnitude of it is calculated as delta V over delta D. So we do know that the electric field between the two parallel plates is a constant, is uniform. So this ratio delta V over delta D is the same in between 2 points in this parallel plate. So this ratio delta V over delta D is equal in each point in between two parallel plates. Okay, so now let's see if the electron will make it toward the other plate. So the motion of the electron is collinear with the electric field strength, which means that, as we said, we will apply the conservation law of energy. So what we have in this case is the kinetic energy of the electron is eaten up, quote unquote, by the electric potential energy of the between the two parallel plates, and this will be equals to the final kinetic energy. Since we are asked if the electron will make it to the other plates, let's see what sign this value has. If it has a positive value, that means that kinetic final has a certain value. So the electron, even though that the kinetic energy is eaten up by the electric potential energy between the two plates, is still able to reach the other plate. If it is negative, that means that the electron doesn't reach the other plate, is not able to reach the other plate. And based on that, we will find where is it stopping. So in this case, we'll have 1/2 mass of the electron, that is 9.11 times 10 to the power of negative 31, times 3.43 times 10 to the power of 4, the whole thing to the power of 2, minus the change of voltage, which is 120, times the charge of the electron is 1 elementary charge, so 1.60 times 10 to the power of negative 19. Let's see now if this is positive. So if this is positive, that means that the electron, in our case, the charge, will reach the other plate. And if it is negative, the electron, in our case, will not reach the other plate. What we are finding on this case is what is the final speed of the electron, and what we are finding on this case is where is it stopping. How far from the entrance is it stopping? Okay, so let's enter this in the calculator and see if this expression here, this whole expression here, is a positive or is a negative value. And what I have is a negative value. So what I have here is a negative value. So the calculator is telling me that this is equal to negative 1.92 times 10 to the power of negative 70. This means that what the path that the electron in our case is doing is something like this. It is moving toward the negative plate, and then at a certain point is it stopping. So this will be the path of particle. And what we are doing is we're finding where is it stopping, how far away from the entrance point is it stopping. So here is it stopping. Okay, this is very similar to you throwing an object up in the air, straight up in the air. And then what do you see is that it reaches the maximum and then it comes back to ground. This is exactly the same thing. Okay, so let's see now. It's similar to the example that we did even before. What voltage will it stop? Will stop at that voltage where the electric potential energy is eating up, quote unquote, the initial kinetic energy. So initial kinetic energy, we did that example right before, is equal to delta V, that is stopping, times the charge of the, in our case, particle is electron. So 1/2 times mass of the electron, 9.11 times 10 to the power of negative 31, times 3.43 times 10 to the power of 4, the whole thing to the power of 2, is equal to the voltage that will stop the particle times 1.60 times 10 to the power of negative 19 coulombs. Let's figure out now what is that voltage that will stop, and then after that it's easy. We'll see. What I have here is 3.35 times 10 to the power of negative 2 volt. So what this is telling us, saying that the change of voltage between delta V stop, between this point where the particles start to turn around and the negative plate, is 3.35 times 10 to the power of negative 2 volts. Okay, why are we doing it from the negative? Because the voltage is gradually increased from negative toward the positive until it reaches the difference of voltage between the two plates. So it starts at, let's say, 0 in this case, and then it goes up to the positive plate, that is 120 volts. On this case, we'll stop barely close to the negative plate, and then we'll head toward the positive plate. So now, we said that magnitude of the electric field strength is delta V total between the two plates over the change, the distance between the two plates, but the distance total. But at any point between the parallel plates, so this is the same. So we can say that the change of voltage at point A, any point A, is over the delta D between the negative and point A, I will say negative and point A, is the same. And delta V of any point over delta D, that is the distance from the negative to that point, to that any point. In our case, what are we interested is the delta V that stops the particle over the delta D that stops the particle, which is from the negative to where the particle is stopping. So the ratio that we will use in that case will be those two, because this is what we are looking for. Where is it stopping? So in our case, we will have 120 volts over the distance between the two plates. I believe it was 4.56 times 10 to the negative 2. 4.56 times 10 to the power of negative 2 is equal to the stopping voltage, or the voltage that stopped, which is 3.35 times 10 to the power of negative 2 over the distance from the negative plate up to the point that the particle stops. So the distance that is between the negative plate and where the particles stop will be cross multiplied to that, you know, so 4.56 times 10 to the power of negative 2 times 3.35 times 10 to the power of negative 2 over 120 volts will be, enter this in your calculator and we will see, compare the values. I have 1.27 times 10 to the power of negative 5 meters. So this is telling us that the distance between the negative plate and where the electron, in our case particle, will stop is 1.27 times 10 to the power of -5. Now you have to be careful to what the question is asking you. It is asking you how far the electron is traveling or where is it stopping from the negative plate. If the question is asking where is it stopping from the negative plate, will be this one here, if they are this value here. And if they are asking you how far is the electron, in our case, traveling, then you will go 4.56 times 10 to the power of -2. That is the distance between the two plates, minus 1.27 times 10 to the power of -5. So 4.56 times 10 to the power of -2 minus the answer. And we will have 4.55 times 10 to the power of -2 meters traveling in between the two parallel plates. So this is the first part of the parallel plates motion, charged particle entering into parallel plates. We'll continue with the second part in a moment.